Thank you. Okay, first I would like to thank my friend Dan Zanfran, and to thank also the chairman of the Department of Mathematics of the KAIST, Professor Kim, and people here, okay, for the invitation. Okay, so today I would like to talk about the applications of algebraic geometry in information theory. Okay, and I can use this. But I cannot use this. I can use this. Okay, okay. Okay, so I will, okay. In coding theory, okay, first, if you take something like this in a vector space, we define which we call the Hamming distance of two elements, x, y. The Hamming distance is the number of a component where xy is different from, xi is different from y, comment on dit y, okay, okay, yeah, different, yeah, different, but you said you okay, the difference, okay, and okay, and we define also the weight of a code word like the number of okay, the number of I where it is different from 0. Okay.
Can you remind us what FQ here is?
Okay. FQ is a finite field, okay, with Q elements. Okay. Okay, and C, H is in fact from Hamming. Name. Hamming. I call this the Hamming distance because of Hamming. It is a notation. Okay, you can call D. Okay. And in coding Turing, we are looking for code which has large minimal distance, because with this we can correct a large number of code words. Okay. So this is the outline of my talk. First, I will recall here some notations. I will show you the construction of the code CH. I will use also some result of hyperplane sections in the projective space of n dimensions over the finite field. 3, I will recall some general result of Hermitian variety. And the 4th, I will study the code C2. Here H is 2, or on the Hermitian surface. Hermitian surface has a variety which has a large number of points. And I will study also the code on the Hermitian solid. Solid is very hypersurface in the projective space of 4 dimensions. Okay, and based on what has been done here in this part, le pointeur, c'est comme. Okay. So based on what has been done here and here, I would like to generalize my result in the projective space of n dimensions. When n is odd, when n is even. Okay, and we have another kind of generalizations. Okay, first, what we should know. Okay, FQ is the finite field with Q element, and V is the affine space of n plus 1 dimensions, and Pm is the corresponding projective space. The number of points of this projective space is this, Pn. This is the expressions of Pn. And I called Fh the set of form of degree h on V with coefficients in FQ. By form of degree h, we need to understand that homogeneous polynomials of degree h. And if we take f a homogeneous polynomial of degree h, we call by Zf the set of 0 of point. And on the set of 0 of the hypersurface S, we have some result I need to recall here. These results have been proved by Warnings in 1939. Okay, a lower bound for the number of points of an hypersurface of degree d is given by this. This is a lower bound. It equals 0 if d is less than n, and equal p n minus d if d is greater than, strictly greater than n, and if d is less than n.
Sorry, this is the lower bound for what?
The number of points of f is a hypersurface of degree d.
Of degree D.
D, yeah. And Pn, this is the expressions of P here. And in 1974, okay, here, when the hypersurface is singular.
So, sorry, it's a lower bound.
Yeah, lower bound. The number of points is always greater than this.
Okay, 0.
Yeah, and or, okay, equal this or this. And in 1974, in the case of non-singular hypersurface, Deligne give a result. The result of Deligne is the number of points of an hypersurface of degree d is less than b q n minus 1 over q, where b is equal to d minus 1, the Betti number. The proof is complicated, use or some cohomological result. Okay. This is for non-singular hypersurface.
What is n? The number of points?
We live here now in the projective space of n dimensions.
No, capital N here.
N, yeah, the number of points of,
Is it n?
yeah, okay.
Could you remind me what pi n minus 1 is?
Huh?
Could you remind me what is the number of pi?
Here, yeah,
Oh, that's
yeah, yeah,
oh, I see.
yeah, okay, okay. And I think in 1989, this is lower bound, upper bound for non-singular hypersurface. And in 1989, Serre, Jean-Pierre Serre, proved this result was conjectured by Tasman. He proves that if you have an hypersurface of degree d, the number of points is less than, okay, you can say n, is less than d qn minus 1 plus pn minus 2. This result was conjectured by Tasman and proved by Serre, Jean-Pierre Serre, and Sorensen. I will use several times this result in my talk. And this upper bound is reached when the hypersurface is in fact a union of D hyperplane, okay, which meet in a subvariety of codimension 2. So now everything is clear. Thank you. Okay, this is the construction of my code. I want to construct a vector space. We take X, which is a variety, okay, an algebraic variety, and N, big N is in fact here, the number of points of this variety over the finite fields. And we define the map C from the space of all polynomial of degree h to Fn. And for every polynomial, we will evaluate this polynomial to the point of our variety x. C is in fact a linear map. Therefore, the image is a vector space. And we call the image the code CH. Okay. And if we take now a code word, which is an element of our vector space, we define the co-weight. Okay? The co-weight is in fact...
Sorry, I don't understand. The value at points is well defined?
What?
The value of an element f in there evaluated at a point?
Yeah.
This is well defined? You don't have the prime of up to a... Is it well defined? Or is it
okay.
Up to a constant, multiplicative constant?
Thank you. I need to precise this. Okay. Thank you. Okay, it's a good question. Okay, so if you live in the projective space, thank you, it's a good question. If you live in the projective space, Pn, we can write Pn equal the union of where UE is equal to xi minus 1 xi, okay, where x0 to xi minus 1 equals 0, and xi is different from 0. And if you take a point P in Pn, okay, this point here, the union of the ui is in fact, it is a partition of P. So if you take a point here, okay, and you want to evaluate this point, you can write that it is Fp. You can write it is this over xid, and it is well defined from this. If you take this construction, it is well defined. I can.
The degree?
Yeah, d is the degree of the polynomial. Okay, I can give you if you want. Is okay. Okay. Good. So now, okay, if you take an element of our code CW, we define the co-weight. The co-weight is the number of points where the polynomial should be f should be 0. And the weight is the difference between the number of points of x minus the co-weight. And the minimal distance is in fact the minimal, the difference between x and the maximal of the co-weight. And the length of the code, this n. Okay, so n is the number of points of x. The dimension is the dimensions of this vector space. Okay, the dimension is given by a result in linear algebra undergraduate, and the minimal distance, okay, is equal to this. So to have a code with large number of code words, okay, we need to have an injective map. And if the map is injective, the dimensions of our code is given by a result in combinatorial analysis. Okay.
I'm sorry, I'm really lost. What is it? Is code word is the same as the variety?
A code word.
The code word
here is an element of this.
Ah, okay.
Yeah, is an element of the vector space of here, of this.
Okay, so you have a one variety and one form, and you evaluate.
Yeah. Okay. Okay, and here, okay, since I have defined the code, or I can write here.
Yeah.
Okay, I have defined the code of CH by evaluate polynomial of degree h. Now I want to specialize on C2. C2, I will take all of the polynomial of degree 2. Polynomial of degree 2 are quadrics. So I need to give some result of quadric because I will study the intersection of quadrics. What you need to know. If you have a quadric which is a homogeneous polynomial of degree 2, okay, a non-degenerate quadrics. First, I want to give some result on quadrics. If we live in Pn, okay, or P del, okay, and we take a quadrics non-singular quadric. Okay, we define an invariant which we call the projective index. The projective index of this quadric is in fact the largest dimensions of linear subvariety contained in these quadrics. And when we live in the projective space of odd dimensions, we have two types of quadric. Quadric which have projective index equal L, and quadric which are projective index equal L minus 1. Here we call these quadrics hyperbolics. And here we call these quadrics elliptics. And the number of points of this non-singular quadrics is equal to P plus QL. And here the number of points is P. So these have more points than this. And when you live in a projective space of even dimension, Q non-singular is what we know. We have only one type of non-singular quadrics. They call parabolic quadrics. The projective index is equal to L. And the number of points, all the parabolic quadrics, non-degenerate parabolic quadric, has the size of an hyperplane. So P, and all degenerate quadric, which has a non-degenerate quadric, a parabolic has base, has also this size. So now I can give some results. The result of Primos in 1951 says that if you study the sections of a non-degenerate quadrics, okay, with an hyperplane, okay, we obtain in Pn we obtain a non-degenerate quadric in Pn minus 1 if the hyperplane is non-tangent, and you obtain a degenerate quadric of maximal rank if the hyperplane is tangent. But this result is not sufficient, and it was completed by Jacques Wolfman in 1975. I want to give you the example why this is not complete. Take for example in P3. In P3, what I told you here, we have two types of non-degenerate quadrics: elliptic quadrics, which has only point, and hyperbolic quadrics, which has line. And if you study the sections of this quadric with an hyperplane which is tangent, from the result of both Primos, we obtain some things in P3. We can obtain this or this. Okay, so to that, but from the result of Jacques Wolfman, okay, here from the result of Jacques Wolfman say the quadric you obtain has the same type as the non-degenerate quadric. So from the result of Jacques Wolfman, since the non-degenerate quadric is elliptic, we obtain only this. We cannot obtain this. So this is what you should know on the sections of quadrics. Okay, we have also some results on Hermitian variety. Okay, here in this paper, the study Hermitian curve. In these books or paper, they study also Hermitian variety. Hermitian. Okay, I want to define. What you should know is the same like in the field of complex number, but we work on the field of a finite field. I want to take some. to be clear with me what I should do first, quickly. Oh. Okay. Okay, here we take, for instance, H belong to FQ squared, okay? And we define the conjugate of H equal, like in the complex number, equal HQ, okay? And we define a power Q. Yeah. Yeah.
What is that?
H power 2.
QF.
Yeah,
What is
QF.
squared? Is it a Q squared or?
Q square. This is Q square. F Q square. Okay. And H power Q. Okay. And here we define a matrix. Okay. 0. Okay. Y belong to this. Okay. And H is Hermitian, like in the case of complex, if and only if for, okay, this. Okay, and
is it an involution?
huh?
This conjugation is it an involution?
Why? What?
Is it?
Q squared is, yeah.
Is it an involution if you apply conjugate?
Yeah, the same thing, like in the case of complex number. Yeah, the same things. Okay, and okay, here we can define, if you take, for instance, X, this is the transpose, and a matrix, and we take a point, okay, a point, this is C is a point, and we take C, I think C0, C1, CQ, Cn, okay, and the power of CQ is C0, C1Q, Cnq, okay. Here we have a polynomial of degree Q plus 1, okay. And a Hermitian variety is some things like this. Okay, a polynomial we can write with an Hermitian matrix.
Sorry, what is C? What is X in this?
X is the, I want to have an hypersurface. I want to have the equations of a polynomial. When I write X, that means X0, X1, and Xn. Okay? And H is a...
Where do they live? This Xi's, where do they live?
Where H? In FQ
Yeah. And FQ?
is a finite field. FQ square is a finite field. Okay.
And C?
C is a point. Is a point.
What do you mean point?
Oh, is a point of Pn.
Pn?
Yeah, a point. Another point, okay? I want to say that from here, okay, we have a polynomial of degree Q plus 1, but it's not it's a particular polynomial, which we can write like in this form, okay? This is a constant, but point you choose.
Right. You want to make a polynomial, yeah, C.
So you say the polynomial, but what is the variable?
Ah, okay. So I change. Okay. I'm okay. Okay. Yeah. Okay. So, okay. So, wait. Yeah. I'm okay. Yeah, understand. Okay. So if you want some things like this, we can put here. In my understanding, okay, if you want some things like this, if I take x, for instance, okay, in my case, if here I put, I forget this, in my case, if I put this, for instance, x1, if I leave in equal 0, okay, here, q, if this q equal t square, this is an emission hypersurface, because we can write like the polynomial x q if t and h, okay, c a constant t, okay, and the some things equal 0, and here c equals c0, c1 is a constant. This is the transpose. Okay. X, if you take x. Okay, so 1966, okay, the result which had been obtained for quadrics, the same result have been obtained also for emission variety. Stadio, the section, hyperplane sections of emission variety, non-tangent case, Bose-Chakravarty, in 1971 by Chakravarty. And there are 3 books, or famous book of James Ishveld on emission variety. Okay, now I come to my topic now. I want to study the code C2 over the emission surface. This is the emission surface. And the number of points of this emission surface, it is a surface in P3. Here, I precise that Q equal T square. Okay, and the number of points have been computed in 1966. Emission surface, emission variety are interesting in arithmetic because they have large number of points. We cannot find some kind of hypersurface of the same degree which has much more points than this variety. And the map I have defined a map. What map? At the beginning of my slide. Okay, this map. Okay, I need to make it injective. So if you use the result of Tasman says so and then here, this happen bond, we can prove that when h is less than t, okay, when h is less than t, the map C is injective. In the case h equal 2 and t equal 2, that means we are studying the section of quadrics with emission surface over the field with 4 elements. This work has been done by Randolph Tobias in 1985 and Paul Spoo in 1986 in North Carolina. But they use a computer program to find the minimal distance of the code and the weight distributions. The weight distribution of a code is this. The weight distribution of the cause is this. Is a couple like this, where HWI is the weight and AWI is the multiplicity. In fact, the number of code weight reaching this weight. So by a computer program, they find all the weight distribution of this problem. And in 1991, Sorensen, which is working in algebraic geometry, proves that we don't need computer programs to find the minimal distance, because we can compute by some technique of mathematics the number of points in the sections of the emission surface and the quadric surface. and he completes the result and he formulates a conjecture. The conjecture said that the number of points in the sections of emission surface, every surface, is less than this upper bound. And this upper bound is reached when the hypersurface has the configurations of Tasman cell Sorensen. And second, all the hyperplane, here we live in P3, therefore the hyperplane are plane. All the planes are tangent to the surface. And second, the subvariety of codimension 2, which is here a line, meet the Hermitian surface in T plus 1 point. This is the conjecture. And in 1993, this is a workshop in France, Lumini, a biennial workshop. Gilles Lachaud proves that he gives a result for the number of points of an arbitrary algebraic set of dimension d and degree, a given dimension and a given degree. And when you use the result of Gilles Lachaud, you prove that in this case, the number of points is less than this. But unfortunately, this point, the upper bound of Gilles Lachaud is larger than this. So now I want to prove this conjecture in the case of quadrics by using the projective classifications of quadrics. So what you should know is that for quadrics, okay, this is what has been done by computer program in the case H equal 2 and T equal 2 over the field with 4 elements. This code is an even weight code. This is all the weight of this code, okay? And these are the multiplicity of this code. I will prove this, but they use computer program. I will prove this by mathematical argument, not computer tool. Okay, the resolutions of the conjecture. For H equal 1, H hypersurface of degree 1 are hyperplane here. So we use the result of Bose and Chakravarti for the sections of emission variety by hyperplane. And the conjecture is true. Okay, for H equal 2, here I use the projective classifications of quadric. I tell that here we have two types of non-degenerate quadrics, elliptic quadrics here and hyperbolic quadrics. And here we have a quadric which is a repeated plane. Okay, and here we have quadric which are union of two planes. This is, in this case, the hyperbound of Tasman cell Sorensen is reached here. So I would like to show you the techniques of this case and only this case. Okay. Okay, this is some value, okay, for the number of points in the sections of the Hermitian surface and the quadric surface. This is the first large number of points I find, the second large number of points, the third, the fourth, and the fifth. And now, okay, in this case, when Q as this configuration reach the Tasman cell Sorensen, which is a union of two hyperplanes, I use these techniques. Okay, everybody know this, and I can compute. Here we should put L. This is L. Okay, and we need to know what should be the value of this, because we consider the three cases. Okay, we consider the three cases. Here, H1 can be tangent to E, H2 can be tangent, or H1 cannot be non-tangent, H2 non-tangent, and we can change the role. So we have the three cases. When the two planes are tangent, the second case, one is tangent and the second is non-tangent. The third case, the two planes are tangent. And in each case, we have three values which can appear. because when we study the sections of a line with the Hermitian surface, but generally we know that if you study the section of a line with a surface, okay, in P3, the line can be contained in the surface first. Second, if the line is not contained in the surface, okay, the number of points of the line and this surface can be at most the degree of the line, the degree of the hypersurface. Therefore, here we can have L intersections give L contained in X, or L intersection is less than T plus 1 point. But we can prove that it is equal to L, or it's equal to T plus 1 point. Therefore, here we have three cases. But in fact, we can control all the three cases. Not all the three cases, the three values can appear. Here we can have two values, here also two values, here also two values. But in fact, from the 6 values, 2 are equal. So we obtain 5 values for the number of points in the sections of X and the quadric surface. But this is the result I use in the case of higher dimensions. But in the case of P3, no need to use absolutely this result. Okay, now I want to study this case, the section of elliptic quadrics with the Hermitian surface. We know that the elliptic quadrics, okay, I need to go. We know that the elliptic quadrics does not contain line. First, if you suppose that it is equal to 1 point, it's okay because 1 point, 1 is less than this. 1 is always less than this value. Okay. And second, so we can suppose that contain at least 2 points. If you suppose that it contains at least 2 points, P1, P2, okay, we live here in P3, okay, we can take the line defined by the 2 points, okay, and now we take all the plan from this line, okay, they are in fact plan, HI, they are in fact Q plus 1 plan from L, okay, from L, and the union of this Q plus 1 plan is equal to P3. So instead of study the sections of this in general in P3, we can study locally in each plane. Therefore, we have this. The intersection of Q and X is equal to and we can say that it is also or if you want, we can say that it is equal to this Q intersection if and intersection if and this. And here we live, this is a plane, we live in P2. It became a curve. And here it became a curve also. So we have a curve. And we can use now the result of Chakravarti. If it is tangent, we obtain a singular curve. If it of rank 2, if it is not tangent, we obtain a non-singular curve. And here in this case, what we should obtain? Okay, so we can obtain, okay, in the case, this case, we can obtain this. this or this. But when, if it is, in this case, we can obtain this, this, or this. But I want to prove that we cannot obtain this. First, because in the elliptic quadrics, we cannot have line, therefore we cannot have this case. And second, we have supposed that it contains at least 2 points. Therefore, here we cannot have this case, and we have only this case. And now we have a non-singular quadrics, so a non-singular curve, projective curve, which is irreducible. And if you study the section of this, we use the theorem of Bézout. The number of points is less than t, the products of the degree, so 2 times t plus 1. And here also it is a cone. And this cone, in fact, it is in fact, here, it is in fact a cone. This cone is this, P0, 1. This is a point. And this is in fact a set of t plus 1 point. So it is t plus 1 line. So here also we have t plus 1 line. And we want to study the section of this. Every line must meet the conic in at most 2 points. Therefore, the number of points here in the section of this and this is also 2 times t plus 1. So here we have 2 times t plus 1. Therefore, for each case, we can say that the number of points is less than q plus q and we can remove also the 2 points because the 2 points are here. And we have finally q, and if you compute seriously, we can prove that it is less than the value I have precise before. So this is the first number, the first point, the first weight, okay? The first weight comes from the first weight comes from this. The first large number of points. This is the second large number of points. The third large number of points. Okay. So this is the first weight. And I compute also. I give the descriptions of code weight reaching the first weight. And I compute the multiplicity. This is the second weight. And the descriptions, there are 3 types of quadrics giving the second weight and the multiplicity also. This is the third weight, the multiplicity, and this is a conjecture on the fourth and the fifth weight, which should be proved, okay, which I prove also. But let us remark one thing, okay, here, okay, here, what you should remark, look at the first weight, the first weight is divisible by t, the second, the third also, and if the conjecture is 2, the fourth and the fifth. But we can prove that all the weight of this code can be divisible by t, and we will generalize this result in a higher dimension. We use the result of Nicolas Cat on the divisibility of a family of polynomial over a finite field. Okay, and some indications. I have proved also the conjecture in the case h is greater than 3, and there is a line in using the same techniques called. I prove that the hyperbole in the number of points of the section of an Hermitian surface, and every surface of degree h is less than this. Okay, and when there is a line in the intersections, when there is low line, I'm working with 2 people in Singapore. Okay, we have some little result. Okay, now this is the code on the emission solid. Okay, emission variety in the projective space. This is the number of points. We use the same technical like in P3, and this is an estimation, a lower bound on the minimal distance. Okay, but here I will give a proof of, I will find the exact minimal distance. The exact minimal distance should be this T7 minus T5, and we cancel this, and T minus 3, this, and we cancel this. Okay, and here are also the classifications of quadrics in P4. P4, we have only one type of non-singular quadrics, parabolics. Okay, and I use the projective classification. According to the projective classification, we have three types of quadric. Quadric with projective index are 3, quadrics with projective index are 2, and quadrics with projective index are 1. Okay, projective index are 2. Okay, here, projective index are 2 means that the quadrics is a union of a plane. And we know that when we study the section of a plane with an emission variety in P4, this is the large number of points. Therefore, since quadrics with a projective index equal to R at most union of Q plus 1 plane, we get this as the large number of points. Or in the case of quadrics with projective index equal 3, which are union of hyperplane, I use the same technical result of Bose and Chakravarti. Here I use the same technical like in the previous case in P3. Okay. Okay, the same technical, and in the case of a projective index is equal to 1, these are these quadrics. We have two types of quadrics. This quadrics, which is a cone, and this quadric, the parabolic quadrics. Okay. Okay, I consider the case where there is no line. Okay. This is my technique to find the number of points. And I consider the case where there is a line, Q is degenerate, I find this hyperbound. And the other case, okay, this is the, so my technique is to make that, to use the result which has been obtained in P3 to study P4. So this is the value I obtained here. Okay, this is in the case of Q contain exactly, X and Q contain exactly one line. In the case of where is at least two lines, I compute the value. Okay, and I consider the case where X and Q contain at least 2 second line. Okay, I use also the same techniques, but here, instead of taking points, I take line. Here point become line, and I have a line, and I take the plane from the line, and I take now the hyperplane, and I have also Q plus 1 hyperplane, and I study the section of Q and X in each hyperplane. It is the same techniques, and I find this value. So this is what has been obtained, the first weight, the second, and the fifth weight. Okay. Okay, I compute also the multiplicity, okay, of this code. And now, based on what has been obtained, I have made a conjecture on the distributions of the minimal weight. Okay, the minimal weight are given by quadrics which are the configurations of Tasman, Cesur, and Sen. This configuration, union of D hyperplane, which meet in an union of a subvariety of codimension 2, and here each hyperplane is non-tangent, and the plane of the plane of intersection of the hyperplane meet X in a non-singular emission variety. In P3, what you obtain in P3, we have this. We also have this. But what changed in P3 and P4 is that in P3, the plane are tangent. And in P4, the plane are non-tangent. So this result will be general also in P odd and P even. So the conjecture is true in the case h equal 1, h equal 2, okay? Or we don't have we are trying to work in the general result. Okay, in the case of Pn, okay, based on what has been obtained in P3 and P4, we formulate the conjecture that the first fast weight, okay, are given by quadric, which are union of two hyperplanes, just 5 minutes. And the first weight, this is the descriptions of the first weight. When n is odd, what I told you before, the hyperplane are not tangent to x. And when n is odd, the hyperplane is tangent. In the case of P3, we live here. In the case of P4, we live here. And in both cases, we have this. The subvariety of codimension 2 here, okay, is in fact a meter x in a non-singular Hermitian variety. And after the fifth way, we cannot have a quadric, which is union of hyperplane, giving code word of fifth weight. So the distribution stop at the first 5 weight. Okay, the conjecture is true for n equal 3, also for n equal 4. And recently, Professor Leo Storm and his student Hanja Alez have proved this conjecture under the conditions, the hypothesis that n equal big tau of q square. Okay, and okay, here the motivations, okay, in 1981, people study the sections of Hermitian variety, but Hermitian curve. The motivation was not in coding theory. They found some result, but they could not compute the computations. But here what is interesting is that because the motivation is coding theory, we can generalize the result. This is some result on Hermitian curve and surface. Okay, we can find here. And in this paper, we study the sections of Hermitian variety in Pn. We generalize all these results. Okay, this is the big theorem we have obtained. Okay, we prove that if the sections of two Hermitian variety is the number of points is larger than this, we can find an Hermitian variety which is in the pencil defined by the two Hermitian variety which contain a q+1 hyperplane. And since we know how to control hyperplane, we can find some interesting results. Okay, so here, this is what we obtain, the fourth weight, the multiplicity. Okay, the multiplicity. And this is the big theorem I obtained with my boss in Singapore. In P3, we remark that all the code words are divisible by t. Okay, and in P4, the result, the weight are divisible by t squared. Okay, here we give a general result. When we study a code on a Hermitian variety, okay, in Pn, a non-singular Hermitian variety, we find that, okay, all the weight should be divisible by t power lambda. Well, lambda, okay, lambda is has this value. E is the integral part of n h. This is our big theorem we obtained in Singapore. And based off our experience on the study of the computing of a number of points of algebraic set, we formulate this result, which is a generalization also of the result of Tasman-Serre-Sorensen. Our result states that if you have an algebraic set of degree D and dimension S, okay, the number of points is always less than this formula. There are several results, but our bond is much better than the bond, but it is a conjecture. Okay, this is some reference, okay, on our work. Okay, another reference. Okay, thank you for your attention. And happy New Year. Manse is a Korean word, I think, 10,000 victory, something like that. Okay, thank you.
Yeah, any questions or comments? No, then we can speak.
Okay, thank you.